All right, now we get to move on to what I think is the fun stuff. So we're going to move on from kinetic energy and activation energy to potential energy and activation energy. And potential energy is going to be something that we focus on for the rest of this unit. So, potential energy is the energy stored in a system. The potential energy of a chemical system is related to the energy of the electrons in the chemical bonds, as well as the number and type of atoms in the molecules. So, like I was saying, as we proceed in this course, we're going to be looking at potential energy and not kinetic energy, and then we're going to be drawing potential energy diagrams instead of kinetic energy diagrams. So, let's talk about how we build a connection between kinetic energy and potential energy. When you're going to have a reaction, the molecules collide. But before they collide, the colliding molecules are going to approach each other, and there's going to be this weird repulsive force. So, repulsive force is when they push against each other. So, you've got these molecules whizzing towards each other, and then they get closer and closer, and they start repelling, so wanting to go the other way. What would happen to the kinetic energy of those molecules, right? They're coming in hot, and then they're getting repelled, but still wanting to go towards each other. And so, what's happening is that the kinetic energy is decreasing. So they come in hot, and then the repulsive forces are slowing down their approach. As they push against the repulsive force, the potential energy is going to increase. Should be a comma there. So as they push against the repulsive force, the potential energy increases, kind of like a compressed spring. So if you think about it, like they just really want to get there, right? And so the kinetic energy is converted to potential energy. But the total energy is going to be constant. So if you've taken physics courses, right, it's that idea of the law of conservation of energy, right? Energy is neither created or destroyed, it's just converted. So this kinetic energy of motion is moving or changing into this potential energy that they're going to contain. So from a graph, right, you're coming in with all of this kinetic energy, and then it's losing its kinetic energy, and then after the reaction happens, the kinetic energy will start increasing again. Whereas the potential energy is the opposite. The molecules are coming in without a lot of potential energy, but as they start approaching, the kinetic energy decreases and the potential energy increases until that reaction is going to happen, and then they can break apart, potential energy will decrease, and then everything will go along. So, this potential energy diagram is what we're going to get used to drawing. So, at the beginning, you have reactants, right? The reactants are approaching each other, and then they're going to gain potential energy as the molecules are repelled or as they slow down. And then what's going to happen is at the top, they're going to contain the most potential energy, and this is where they form what we call an activated complex. So, an activated complex is if the reacting molecules can gain enough potential energy, i.e., they have sufficient energy for a successful collision, then an activated complex or an intermediate molecule will be formed. Then there's going to be this whole new bond rearrangement that's going to happen. The reactants are in the process of forming to a product. And so this activated complex has a very short lifespan. It's unstable. And we show it. I'll just keep staying away from that diagram. But if you look here, so we've got our reactants. And then here we have our intermediate molecule or our activated complex. I kind of like activated complex better because it's like an activation happened. There had to be sufficient energy for this complex to be activated, right? But it's sort of an intermediate between the reactants and then over here, your products. So once those bond rearrangements happen, then the potential energy is going to decrease and you're going to have this formation of your products, which is either going to have more or less energy than your reactants, which we'll talk about in a bit. So again, here's your simple diagram. You've got your reactants coming in, they're gaining potential energy, they're forming an activated complex, and then they're rearranging their bonds and coming out as products. Awesome. So let's talk about activation energy. The activation energy is the difference between the reactants and the formation of the activated complex. So the potential energy is the amount of energy that needs to be gained to form an activated complex. So in your diagram, it always goes from reactants up to energy level of activated complex. Okay? And that is your activation energy. So this would be an example of a lower activation energy. I like to think of it as a barrier, like a literal wall. And so these frogs don't have to have as much energy to clear the wall. Whereas this is a higher activation energy. So see how this is a much higher hill to climb. A bunch of these frogs are not going to have enough energy to jump over the wall. So you'd have much fewer products formed and a much slower reaction. So a lower activation is a faster reaction because more molecules will have sufficient energy for a successful collision. More frogs would have enough energy to jump over the wall. Whereas if you have a higher activation energy, this would be a slower reaction because less molecules will have sufficient energy for a successful collision. So yes, those kinetic energy diagrams are important, right? The molecules have to come in with enough kinetic energy to be converted to potential energy so that they can form an activated complex. Okay, but this is the picture we're going to talk about the most. So I've got 4 pictures here, and I want you for each diagram below to determine A, the potential energy of the activated complex, and B, the activation energy. So for the first part, the potential energy of the activated complex, it's simply the amount of energy here. So this is the potential energy of the activated complex. We're just going to say AC, and this one's going to be 100. Now let's figure out our scale. So there's a line, 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 line. So 2 lines to get to 50 means that each one is worth 25 kilojoules. So the potential energy of the activated complex for this potential energy diagram would be 125 kilojoules. Then if we talk about activation energy, it is the energy from the reactants to the peak of the activated complex. So it's going to be the amount of energy that needs to be gained as potential energy. So it's going to be this space here. So it's going to be equal to 125 minus the energy of the reactants, which is going to be 100 kilojoules. Okay, let's keep going for the next 4. I'll do another one with you and then you can pause the video. So for this one, the activated complex has an energy of 100 kilojoules. And for this one, the activation energy is from reactants up to activated complex, which is going to be from 25 up to 100, which is going to be 75 kilojoules. All right, pause the video. Give the next 2 a go. So for this next one, the activated complex has an energy, just making sure my scales didn't change, of 125 kilojoules. And then my activation energy is going to be from 75 up to 125, so it's going to be 50 kilojoules. And then for this last one, my activated complex has an energy of 75 kilojoules, and my activation energy is going to be from 50 to 75, which is 25 kilojoules. Awesome. Moving on to part 2. Part 2 says which reaction or which graph shows the fastest reaction and which graph shows the slowest reaction. So the fastest reaction is going to be one with lowest activation energy, whereas the slowest reaction is going to be the one with the highest activation energy. So the fastest reaction is going to be which one? Well, this one has an activation energy of 100, 75, 50, and 25. So graph D is going to be my fastest reaction, whereas my slowest reaction is going to be the one with the highest activation energy, which is graph A. Awesome. I think that's the end of this lesson. Perfect. Go and try some questions.